Welcome everyone to our TEWI-Kolloquium and welcome our guest Sergey, who came the way from Madrid to foggy Klagenfurt to give a nice talk here. I will especially welcome also the people here on site, and of course those joining remotely. I know there are a few there. And Sergey will give us a talk about, as you see it on the title, RL caching, reinforcement learning caching, I think it's called, a learning-based cache admission for content delivery. And it's good to have you here, first of all, and we look forward to an interesting talk. And the talk is also recorded, so my proposal is that you give first your talk, and then we have a discussion at the end. And of course, also those who are remote, please feel free to come up with questions. You can either talk or write in the chat. We have the meeting over here that takes nice pictures, a nice camera setup, and also of course the audio. And I hope the audio is fine for you guys remotely. If not, please write me in the chat, and then I can probably try to fix it. But now the floor is yours. Thank you for coming, Sergey. And we're looking forward to the talk.
Thank you. Thank you for your kind introduction. After Christian invited me to give a colloquium, I watched the most recent video presentations in your colloquium series. And one of the speakers, Clara Narstedt, Illinois, she spoke about your recent work, recent joint work with Ramesh Sitaraman. So today, I decided to follow in Clara's footsteps and present my own joint work with Ramesh and our respective former PhD students, Vadim Kirillin and IMDEA Sundarajan. So the work is seeking to improve CDN caching by means of reinforcement learning. Caching is a fundamental technique for latency reduction in computer systems. Different types of systems instantiate the technique differently, and there exist many flavors of caching. We study caching in content delivery networks, or CDNs, which deliver most of internet traffic. A CDN is essentially a collection of edge servers placed in access networks around the world. So when the user, when an end user wants to obtain content of a content provider, the user can fetch it in principle from the origin server of the content provider. But this will incur quite often high latency, for example, on the order of hundreds of milliseconds. So instead, the content provider employs a CDN. The CDN caches the content in an edge server in close proximity of the end user and delivers content with low latency, for example, on an order of milliseconds. Another additional benefit of using the CDN is in reducing the long-distance internet traffic. Emergence and great commercial success of CDNs are largely due to getting the deployment model right. So low latency makes the end user happy, which in turn makes the content provider happy. Besides, the use of CDN reduces the burden on the content provider, including traffic costs. Similarly, the access network is happy because it receives less traffic from the transit provider and reduces its transit costs. In fact, the access network typically hosts the CDN's edge server for free. Because the CDN business model captures, provides strong incentives for all the stakeholders to deploy, CDNs proliferated and became an indispensable element of internet-based content delivery infrastructure. So when the economic layer is removed, the good case of using the CDN is quite simple. The CDN associates the end user with a nearby edge server. The end user sends a request for an object to the edge server. The edge server has this object in the cache. In other words, a hit happens. And finally, the edge server delivers the content to the end user with low latency. Unfortunately, there is a bad case too. So if the requested object is not in the cache of the edge server fetches the object with high latency, again on the orders of hundreds of milliseconds, from the origin server before delivering the object to the end user. The edge server also has an option of caching the fetched object so that to be able to serve the object immediately upon subsequent requests. So why would the edge server not have the object in the cache? Right. So to start with, the first request for each object is necessarily results in a miss, known as a cold miss. Right? And besides, it's not cost effective for the CDN operator to permanently cache all the fetched objects. And especially because such permanent storage would provide any benefit at all in many cases. So many, for example, 10% of all requests are one-time wonders, meaning that the same object is never requested again. And in general, the object churn in CDN caching is quite significant, meaning that even popular objects eventually cease being requested. Right, so as a result, the cache is typically sized to some limited capacity, and at any given time stores only some of the fetched objects. Thus, the caching problem is to decide which object the edge server should cache at a given time under the constraint of the fixed cache size. The objective is to maximize the hit rate, which is the fraction of requests that result in a hit. The hit rate closely correlates with the content delivery latency as experienced by the end user. While the edge server has to make admission decisions in real time, they don't have to be instantaneous upon a cache miss. After the miss, it takes a significant amount of time, against hundreds of milliseconds, to fetch the object from the origin server of the content provider. And besides, delivering the object to the end user can be asynchronous with the caching decision. In other words, the edge server can decide whether to cache or not to cache a fetched object already after sending the object to the end user. The caching problem is challenging for several reasons. First of all, the CDN serves a large number of traffic classes, such as video, web, images. The properties of objects within traffic classes are quite diverse. Even within the class, properties vary a lot, and in particular, object sizes tend to be different, and it turns the caching problem into an intractable knapsack problem. Different object sizes are not the only complication in caching. For equal size object, last probability developed an optimal offline algorithm. So when the cache doesn't have enough space for all the object, this algorithm discards the object that will not be requested for longest time in the future. So in this toy example, we have the cache that can hold up to 2 objects, and at a given time, the cache contains the blue and red objects, and there is a request for the green object. Right, so this algorithm sees that the red object is the one which will not be requested for longest time in the future, and makes an optimal decision to discard this object and replace it with a green object. All right, so unfortunately, we don't have this knowledge in CDN. CDN caching is an online problem, so the unknown future prevents us from having an optimal solution, and we have to rely on heuristics. All right, so these heuristics can look only at the historical data, what happened in the past, and usually they look at such aspects as such factors as the recency, basically time elapsed since the last request for the object, or how frequently past requests for the object arrive, or the object size. As we basically see here, this is our two examples. If we go back to it and look, without knowing the future, a heuristic might decide that, well, let's keep the red object there. It seems to be popular in the past. Maybe it will continue popular in the future. Or let's discard the blue object because it was requested a long time ago in the past, without realizing in the future will become popular again. So we can see how these cases go wrong, and unfortunately CDN caching, the situation is the same. So CDN caching algorithms are suboptimal heuristics. So this prior solution on caching, CDN caching, can be viewed as containing two components: an admission algorithm and eviction algorithm. So the admission algorithm decides whether to admit or not to admit a fetched object into the cache. And the eviction algorithm decides which objects to evict, to discard from the cache to make space for the new admitted object. The most common policy for admission is to admit all objects. This policy is so common and implicitly assumed that it doesn't even have a standard name. So in this work, we call it admit all. Its commonality might be also a reason why that caching eviction policies are typically known under the name of cache replacement algorithm, which kind of focuses on the eviction part of the problem. Second heap is a simple admission algorithm implemented by Akamai in its production CDN. And this algorithm uses two Bloom filters for simple implementation and admits an object into the cache only upon the second or subsequent requests within the time window. So in other words, second heap avoids caching one-time wonders. Adapt size is admission algorithm that uses object size as a feature and admits only those objects that size smaller than some threshold. And this threshold is adaptive. Its adjustment is based on a market model. On the eviction side, the research has been much more extensive. It is a huge amount of work, including a least recently used LRU algorithm, which evicts the least recently requested object. So in the reality, many of these more complicated algorithms are not implemented because of their complexity. And it's very common in most of the production servers to use caching based on LRU. So in this work, our goal is to design a simple admission front end for an edge server that uses LRU for eviction. So our research method is reinforcement learning, or RL. Whereas it's become very common to apply machine learning methods to network systems nowadays, we think that for our problem there is a natural fit, because cache admission can be naturally formulated as an RL problem where request features form a state, the admission decisions represent actions, and hits serve as rewards. There is some prior work on using RL in caching. It's quite limited and pursues different goals and outputs. For example, instead of cache admission, deep cache focuses on prefetching and learns popularity to improve the hit rate by issuing fake requests for answers. Well, there is another body of work, a relatively small body of work, which looks at equal size objects and synthetic workloads. Our work is different by looking at real CDN production traces from Akamai. So within the RL paradigm, there are three broad classes of methods. Temporal difference, or TD methods, which include Q-learning, use bootstrapping and update earlier predictions based on the difference within successive prediction values. In our RL formulation of cache admission problem, the correlation between an action, which is admission decision upon a miss, and immediate reward, which is hit on next request, is weak. As it's very rare in the real CDN traces to have two successive requests for the same object. So as a result, under these noisy reward signals, the estimation of action value is imprecise. Monte Carlo or MC algorithm, they generate multiple samples of long sequences of state action pairs, and they average these long-term returns from the samples in order to update an action value. The problems with Monte Carlo algorithms is that they have large overhead. They have to compute the returns over multiple long sequences just to obtain one state action pair. So the third class, Geographic policy search GPS techniques, they also generate multiple sequences, but instead of averaging individual returns, the GPS methods use these individual returns to segregate a subset of high performance sequences and use these high return samples for searching directly in the policy space for policy that is targeted towards maximizing the return as opposed to providing the average one. So in our work, we designed cache admission algorithm, RL cache, that relies on direct policy search. To capture the RL state, we consider 8 features belonging to 3 common classes: request recency, request frequency, and object size. Actually, looking simultaneously at the features of the 3 classes is one of our contribution. In the past, traditional heuristics look at 1 or 2 features. For example, adapt size looked only at object size to make admission decisions, and the second heat looked only at frequency. The cornerstone of RL cache, feed-forward neural network that outputs the probability of admitting the fetched request into the cache. The training of the neural network is computationally extensive. It's done periodically in the cloud. On the other hand, inference is done in real time by the edge server. Subsequently, I will talk in more detail about each of these elements of RL cache design. So the 8 features we consider in RL cache include 4 features that capture recency by measuring either in seconds or in the number of requests, and also by computing this recency with respect to the most recent request or over a series request in the past. The other 4 features include the object size and the frequency of the request, plus the combination, the fraction, and the product of these 2 metrics. So when I gave an earlier version of this talk before, somebody in the audience asked, so what kind of neural network you have? So this is this slide added in response to the questions from the audience at some point. So we use artificial neural network, which is fully connected. On the input layer, we have up to 160 inputs, which come from 8 features I talked about. Additionally, we consider some historical version of each feature that relies on exponential smoothing over previous requests. And for each feature, we had up to 10 quantization bits. So basically, these then we have 5 hidden layers, which narrow down in the forward direction, and for the hidden layers, neurons use ELU exponential linear utility activation functions. To avoid overfitting, we use L2 regularization. And on the output layer, there are 2 neurons that use softmax activation function and produce admitting probability and not admitting probabilities. So the design of this neural network didn't have an objective to have an optimal one. So we came up with something which works within the available computational resources. It definitely can be done, be reduced in size. In particular, in hindsight, we realized that these historical versions of the features were not really relevant, so we could have removed them from the design. So training is probably the biggest aspect of this work. So what we did, we trained the algorithm over long traces, which contain millions of the requests. And we did it not at one request at a time, but over a larger window of requests. In particular, this variable K captures this size of the window and of the request. So then we use Monte Carlo sampling. We basically generated M samples of admission decision for this window. And additionally, when calculating the reward, which is essentially a loss rate for each of the sample, we consider additional green L requests for the feature. So essentially, in caching, decision to cache or not to admit or not admit an object might have long-term consequences. Because right now you don't get any rewards in given the next few requests, but longer term in the future. So that's one of the feature algorithms. So for each sample, we computed the hit rate over longer sample, and for the these green requests for the future, the rewards were discounted by factor gamma as common in the RL methodology. So after that, following our direct quality search approach, we segregated the top percentile of the samples that provided the highest hit rate and selected them for learning. So which is the next stage. So basically this learning is already done on original red samples, which K request long. So basically we drop the extra L requests, which I used only for estimating the long-term hit rate of each sample. And learning that is done by backpropagation algorithm that use binary cross entropy as a loss function. So this learning is updates the weights of the neural network, and we repeat this process of 3 stages: sampling, selection, and learning until the weights converge within a threshold. Upon eventual convergence, we slide to the next window, and also because the weights change during learning while we go through the trace, every few windows we go and repopulate the cache from the beginning of the trace. So this sequence of 3 slides kind of captured the training algorithm I used. It has a number of hyperparameters, and the algorithm later in the evaluation section will talk a little bit about these parameters and their settings. So training is complicated, and we expect it to be done in the cloud, and the training model downloaded to the edge server. On the other hand, inference using the trained network is simple and can be done in real time. The edge server maintains a database for calculating features, in particular historical information needed to compute frequency and recency metrics. The actual decision is simple. So basically, edge server applies the neural networks to determine probability of meeting an object, and rounds this probability to 1 and 0 to decide to cache or not to admit the object. And additionally, we also use request batching. And remember earlier, I told you that the decision to cache or not to cache the fetch object is neither tight or hard in terms of timing. So it can wait. So we can leverage it in implementation by essentially batching subsequent requests and processing together. So this provides some benefits from pipelining and batching. So it's deep learning paper, right? So it's data-driven, so a big portion. I think the contribution of work is also from the evaluation. We use traces from Akamai's production CDN server, and in particular, on the initial stage of variation, we use traces collected in the Akamai server located in the US. These traces are from web, image, and video traffic classes, and you see the properties, statistical properties of these traces are very different. For example, to provide, if you look at 80% of all the requests, then the percentage of objects which stand behind this request is only 10 for the video trace and 60 for the web trace. Also, within each of the classes, there is also quite significant diversity. Within each class, the object sizes vary by the orders of decimal magnitude. So, to provide an acceptable hit rate for a trace, different cache sizes might be needed depending on the properties of particular trace. So one of the methodological contribution of this work is a notion of active bytes that we introduce to characterize these caching requirements of a particular trace. So let me tell you what it is. So an object is active in a trace between the moment it was requested first and the moment it was requested last. All right. So if you look at any particular time, the active bytes at this time is basically total size of all the active objects. So why is it interesting? It's interesting because if you consider this basic common admit all policy, you decide to admit every object upon its miss, and you reject, you discard this object from the cache when the object was requested for the last time, on the last request. So the active bytes will provide you the amount of cache size needed to provide the maximum hit rate. Essentially, you cannot do it about cold misses, so cold miss always a miss, but the second or subsequent request will be sorted with the cache size to the active bytes. Of course, like Laszlo Beldi's algorithm, it's active bytes is an offline notion. So it's not really helpful for us to actually do caching, but it allows us to understand for each trace what is the reasonable amount of cache, or actually not only reasonable, what is basically maximum amount of cache you need to provide to have a good practice. So basically from this, we said, well, of course, we also don't know if it's less request or not, but if you basically have this amount of cache, basically equal to active bytes, and you combine admit all with a reasonable eviction policy like LRU, then you will expect this admit all will perform well. Okay? And if it's lower than that, it's not. So for example, for this image trace, if we cache the size to 128 gigabyte, right, so we expect the admit all should do well in this case. And if you go to 16 gigabytes, it will not be enough. And looking at the web traffic, the web trace, even 128 gigabyte should not be sufficient. So maybe here also, since we're going to kind of the result, I'll also tell that about the schemes we look at. So I already mentioned admit all, second hit, and the depth size, and we compare it with an arrow cache we designed. For all four of them, first of all, we use LRU as eviction policy, right? So to have the level playing field for all the admission algorithms. And RL cache is the only one which is learning-based method here. So what we do, we train RL cache on the first 10 million requests in the trace, and we test parallel cache and report results here for the subsequent request in the trace. So what do we see? So if we look at the space of 128 gigabytes for image, we did see that admit all behaves quite well. Essentially, provides the highest rate you can rate you can provide, and our RL cache basically needs the performance. Basically, RL cache learns that in these given settings, the cache size is big enough. You have to admit all, which is pretty much optimal strategy. On the other hand, the two other heuristics, the second hit and the size, they kind of outsmart themselves. So they don't admit some object because they think it's one-time wonder, the size is of object is too large, but they're wrong. As we decrease to 60 gigabytes and 2 gigabytes, the policy, the stable policy of admitting every object starts to underperform, but RL cache learns that you just cannot admit everything, you have to admit something more intelligent. It outperforms other counterparts. The same thing here. So we saw for the web traffic that 128 gigabytes is not large enough for admit all to perform well, and RL cache learns the better performance. We also look at the additional data sets that give some diversity to geographic location. So we collect another trace of the web from the web traffic class from another location of the US, and also we had a EU video trace collected in Ireland. In comparison to US traces, which are 4 days long, this was also a longer trace for 17 days. Again, we see different size and popularity distributions for the two classes. In particular, what jumps out that actually EU video has all object size to the same constant chunks. So object sizes are the same in this particular trace. So the difference of the EU video trace is also because it's more intense. So amount of active bytes in comparison to the previous traces you've seen is much larger, 2 magnitudes larger. And it also affects performance. So for example, the cache size of 2 gigabytes become meaningless pretty much for this trace. It's too small. So the cache rates for all the algorithms, they're on the order of 2%. So it's not something which is meaningful for any commercial caching service. Right, and as size increases, we can see that the hit rates improve, and our RL cache algorithm outperforms the counterparts. So now let's make it a bit more interesting, and let's train RL cache on one trace and test it on another trace from different location over different type. Right, and it was interesting within the same region, within the US, it was kind of surprising result, but that RL cache was quite robust in the sense that it still provides high performance despite moving to using data from a different class or different location, and which is nice because essentially it implies that you can train RL cache on data from one location, then I distribute the same model, train model to different edge servers for execution. Unfortunately, this robustness wasn't universal, so when we train on the EU trace and use it in the EU, the result was very different. So training on the low intensity trace and testing it on the high intensity trace did provide this benefits. So here it was not working that well. So it does matter that data type does matter. So also talk about implementation. So we implemented also in CPU and GPU, and essentially we can reduce to 64 microsecond and 4 microsecond respectively with CPU and GPU when we use 1,000 request batches for processing, which basically suggests that it's possible to use the raw cache in production servers. So going kind of beyond performance, but probably try to understand the design itself and whether it's kind of reasonable and reasonable design decisions were made. So we started first by using the relation coefficients for all pairs among our 8 features. So this is the result for EU video trays, and it's not surprisingly the strongest correlation aligned well with the types of features. So basically, size feature, then this block is frequency related features, and this is our recency features, right? Which is not surprising. So they captured somewhat similar notions. And the question, well, do we need really 3 classes or all 8 features? We'll look a bit further. So we'll look at the feature importance using random forest. So it's kind of native mechanism for estimating feature importance, essentially how much average mutual information the feature has with the target, right? And we normalize it to 100%, right? So they were equally important. Each feature in this table will get 12.5%. And what we see that, of course, it's very difficult to interpret how really important they're impactful on performance. They kind of balanced, suggesting that all these features are important to some extent. And another interesting observation that this importance is changing. For example, for EU video trays, the most important feature is from the recency class, and the least important related to size, which is quite intuitive because EU video had only equal size object. And for US1 image trays, the frequency was the most important one, frequency related one, and recency was less important. So depending on actual trace, different features become important. That's kind of a secret of RL cache. Basically, it learns what kind of features are important in any given case. So when we saw this Pearson correlation coefficient and the blocking of this according to the feature class, one question: can you reduce feature set? Do you really need 8 features? Can you use smaller one? So what we have here, the blue bar here is the basic features. Essentially, we take size, frequency, and one of the recency metrics, put them together. And of course, we cannot test all these combinations of the 8 features. We look at some of them. From this table, which I saw before about the feature importance, we just picked the top 3 features in this importance table, top 6 features, and of course, we consider all 8 features we had. So here it shows that the full feature set provides the best performance, which is also interesting kind of to observe here. So this is for EU video. If I didn't include here for the interest of time the result for US1 image tray. So there actually it showed that it's not really kind of you go by the feature importance table and you pick the features, you get kind of improvement, incremental improvement in hit rate performance. It's actually not the case. So in that case, just basic features outperform top 3 and top 6. So it's not only how many features you have, but also how they interact between each other, what impact they have. And just to comment on the right graph over here, so of course, accuracy is not the only thing which is mattered in the algorithms, in the reinforcement learning machine learning algorithm. It's also how much effort you spend in training. So here we measure the effort in terms of number of requests, that's what we call training span. And here it shows how how the accuracy changes. So in this particular case, basically the training effort was somewhat similar. So to bring our relation part of the whole paper closer to the conclusion, we look at the hyperparameters. I told you we have a number of hyperparameters, how they affect them. So the first hyperparameter on the left is K, which is this green number of requests window we used for in our training. So one observation here, as you increase this window size, the amount of training you need to do in terms of requests to achieve some kind of level of accuracy increases. So training, but in general, I know it provides kind of a better overall performance if you train longer, but not universally. So actually, the settings of 50K requests, 50,000 requests for window size, which you use the default, and it was in all our previously reported results, that provided the best performance. So again, it's hard to speculate why it happens, but looks like well, one request is definitely you cannot make reliable decisions, but the expectation that you can look, for example, the whole trace at a time, if you have computational resources for doing so, it's not necessarily optimal. All right, so maybe statistical properties of the data changes quickly enough for the window not to be so large. These graphs on the right show the hit rate and accuracy for the parameter L, which is this, sorry, I think I called K. Green, I think were red, actually, the L extra requests were green. So the extra L request, which we used only for calculating the long-term hit rate. And so here, it's a little bit of a justification of our choice to have this extra parameter there. It also is L0, meaning that we don't look further in the future. When we look at the original K requests, it does perform well and actually trains quite slowly. And the choice of 150K, basically 3 times more than the default size of the window, provided the best performance. So P parameter is also interesting. So I think again, when I gave this talk before, so while you separate and look at the only some top performing subset of all the samples, won't you learn better if you look at all the samples and you can discover some better policies. So I think part of it is actually what kind of algorithm we use. So we use a direct policy search, which essentially searches for optimal policy based on the representative samples. In our case, representative samples are those who provide the high hit rates. Right. So what we see here. So yes, if you use a large number of samples, first of all, you train not as fast. So it's better, of course, to look at the smaller subset. But in terms of performance, it looks like that if you look at all samples, actually, we don't have results here for 100%. If you look at all the samples, actually, just doesn't much at all. For 50% of the samples, you look at the top 50% of the samples. It learns not very good results, but also slow. So there is also some sweet spot of about 10%, which gives you essentially enough diversity to learn the high return policy and trains relatively quickly. And finally, the parameter Q, which is how much we refill the cache to make sure the cache is not polluted with the results based on the previous weights of the neural network. So here the training effort is about the same, but looks like if you don't refill it every window, but every fourth window, that seems to be the good result. So overall, this hyperparameter sensitivity study and the previous study of feature correlation and feature importance kind of shows that the things in the design, they kind of make sense. So let me conclude here. So we propose in this work error cache, the reinforcement learning-based algorithm for cache admission to be used in CDN edge servers. Consider 8 features of the recency, frequency, and size classes. The algorithm works by using direct policy search approach, and it's computation intensive, but it can be used for real-time inference with a low overhead, which is further reduced by request batching. So we related the proposals on the production traces for Akamai CDN. And process will introduce this notion of active bytes to characterize how much cache is needed for good performance on this particular trace, on each particular trace. And overall, we showed that error cache successfully adapts in a variety of settings and outperforms the baselines. Interestingly, it also was robust across traffic classes in the same geographic region, meaning that we can train it on one data from one class and use it in a different location and potentially a different traffic class. And we also had this sensitivity study and look at the feature importance, feature correlation, and overall that part of the relation showed that the selected features and hyperparameters are relevant for successful operation of error cache. So this is open software. You can see here GitHub link that my former student Vadim maintained. So if you're interested, you can take a look. So thank you very much for your time and attention, and I'll definitely be happy to take questions now, or for those of you who want to talk to me later, as opposed to now, I'm also available, so you can always contact me. Public person, so webpage and email address, and so thank you very much.
Thank you. So that's, I think, for the discussion, we can stop the recording. It's usually what we do, but we also can have them more open.
So thank you very much for your attention, and we would be happy to answer some questions.